A data set includes weights of garbage discarded in 1 week from 62 different households. The paired weights of paper and glass were used to obtain the results shown to the right. Is there sufficient evidence to support the claim that there is a linear correlation between weights of discarded paper and glass? We use a significance level of 0.05. If my variables are paper versus paper, it should be linear because it's exactly the same thing. If I have a pound of paper, I'm going to have a pound of paper, and so on. Paper and paper is 1, and glass is 1. First, we want to determine the null and alternative hypothesis. It's always going to be rho equals 0, and rho does not equal 0. Check. Identify the test statistic R. That is this value here. Round to 3 decimal places would be 0.373. Identify the critical values. This is going to be a two-tailed test because we have not equal. If we want to identify the critical values, we go to this table that they're providing. We have 62 different households. The closest we're going to get is 60, and our alpha is 0.05, which is the first column, 0.254, and it'll be plus or minus 0.254. Now we want to state the conclusion. Because the absolute value of the test statistic is 0.254, let me draw a picture so this makes sense. If I have my curve, my critical value is going to be right here and right here. This is negative 0.254 and positive 0.254. Because the absolute value of the test statistic, we're looking at the positive side, it is greater than the positive critical value. These are my critical values. My test statistic is to the right of my critical value. Anything to the right of this or to the left of this is my rejection area. Because the absolute value of the test statistic, which is 0.373, is greater than the positive critical value, that's true. There is sufficient evidence to support the claim that there is a linear correlation between the weights of discarded paper and glass for a significance level of alpha equals 0.05. Why do I say there is enough evidence? First of all, I'm in the rejection area. If I'm in the rejection area, that means I'm rejecting my null hypothesis. I reject that it's 0, which means that it's not 0. If it's not 0, then we do support the evidence that rho is not equal to 0. That means there's a linear correlation between the weights. Use the given data set to complete parts A through C below. Alpha equals 0.05. I want to go to regression, simple linear. My x will be my x variable. My y variable will be y. We're not really conducting any kind of test yet, but we do want to make sure that we have this correct. And we want our most important is the slope. So that's equal to 0. And the alternative would be not equal to 0. Confidence level is 0.95. And I think that's all we need. Compute. First thing, there's these arrows down here. If you want to even make it more clear, you can click on these little boxes down here, and we can change the x-axis to reflect the x-axis that they're giving us here. So our minimum that they're putting in their picture is 0. Maximum is 16. And let's do that. And then we'll fix the y-axis as well. Our minimum is 0, and our maximum is 16. This should look quite a bit more like one of these graphs. We can see there's not a curve here, and there's not a curve here. This is pretty straight. As a matter of fact, this would be a better line. This dot right here is pulling the graph up. If it wasn't for that dot, it would more likely follow a line that looks like that. You can see that would have a different y-intercept, it would have a different slope. Point right here is what's pulling the graph up. As you can see, it's very sensitive to anything that's a little bit different. This is our graph, and as you can see, it looks like C. Let's go back here. Find the linear correlation coefficient R to 3 decimal places, then determine whether there's sufficient evidence to support the claim of a linear correlation between the two variables. There's a linear correlation. Using the linear correlation coefficient found in the previous step, determine whether there is sufficient evidence to support the claim of a linear correlation between the two variables. We looked at the graph and our R value is very high. I'm going to say there is enough evidence, and our p-value is below 0.05. Even if I cut it in half and have a two-tailed test, it's below 0.025. It's smaller than either one of those two. There is sufficient evidence to support the claim of a linear correlation between the two variables. That is true. Check answer. Identify the feature of the data that would be missing if part B was completed without constructing the scatter plot. Choose the correct answer below. The scatter plot does not reveal a perfect straight line pattern. It's pretty good. This is very important that you actually read the question. Identify the feature of the data. The feature of the data that would be missed if I didn't plot the scatter plot. It's definitely not A. The scatter plot reveals a perfect straight line pattern and does not contain any outliers. That's not true. We have a little bit of an outlier. The scatter plot does not reveal a perfect straight line pattern. That's not true. And the scatter plot reveals a perfect straight line pattern except for the presence of one outlier. I'm going to pick D. Question 3. Refer to the accompanying scatter plot. The 4 points in the lower left corner are measurements from women, and the 4 points in the upper right-hand corner are from men. Complete parts A through E below. Examine the pattern of the 4 points in the lower left corner for women only. And we can see that we have these points. Remember, ordered pairs are always X comma Y. Our X is 1 and our Y is 1. Our X here is still 1, but our Y is 2. Our X here is 2 and our Y is 1. And our X here is 2 and our Y is 2. While we're here, let's do the top ones as well. This looks like it's at X equals 8. That means this is at 8. And that point is going to be 9. And then this one will be 8, 10, 9, 9, and 9, 10. I'm going to put these values into StatCrunch. I have 1, 1, 2, 2. And then 1, 1, 1, 2, 2, 1, 2, 2. These numbers up here, I have 8, 2 8s and 2 9s, 8, 9. It doesn't matter the order. 9, 9, 9. Go to Stat, Regression, Simple Linear. We'll choose X for X and Y for Y. Our hypothesis test is 0 not equal to 0. For both the slope and the intercept, the slope is the most important. I can see that my R, which is my correlation coefficient, equals 0, which literally means we have no correlation. Our p-value is 1. Examine the pattern of the 4 points in the lower left-hand corner, that's what we just did, and subjectively determine whether there appears to be a correlation between X and Y for women. There does not appear to be a linear correlation because the points do not form a line. That is the correct answer. Check. Examine the pattern of the 4 points in the upper right-hand corner. Since it's gonna be exactly the same, we're gonna just have the same answer. There again does not appear to be a linear correlation because the points do not form a line. Check. Find the linear correlation coefficient using only the 4 points in the lower left-hand corner for women. The 4 points in the upper right-hand corner for men have the same linear correlation coefficient. The correlation coefficient for the points in the lower left-hand corner is 0. It's coming from right here. That's 0. Check answer. Perfect. And then do the 4 points in the upper right corner have the same correlation coefficient? Yes. Because the 4 points in the upper right-hand corner, no, they don't form a different pattern, form the same pattern as the 4 points in the lower left. That's correct. Find the value of the linear correlation coefficient using all 8 points. Now let's go back to stat, simple linear, x. Everything else was fine. Hit compute. Oh, wow, look at the difference. Now our correlation coefficient for all 8 points to 3 decimal places is 0.982. That changed significantly, didn't it? Perfect. Using alpha equals 0.05, what does R suggest about the relationship between X and Y? Our R is really big. That means these values are correlated. Using alpha equals 0.0, what does R suggest about the relationship? And then there's not sufficient evidence. We have sufficient evidence because look at our p-value. This is the p-value you're going to look for because it has to do with the slope. The slope is whether or not the line shows any kind of a positive or negative correlation. As you just saw, it was very small. There is sufficient evidence because we reject the null hypothesis and use the alternative hypothesis. There is sufficient evidence to support the claim of a linear correlation because the correlation coefficient is greater than the critical value. We know the correlation coefficient, but we don't know the critical value. I have a copy of the table with the critical values. Alpha equals 0.05. We get 0.707. There is sufficient evidence to support the claim of a linear correlation because the correlation coefficient, which we found here, is greater than the critical value. That's true. Let me draw a picture for you. If we have our curve and the critical value is at 0.707 and our correlation coefficient is 0.982. Remember, everything to the right of this value is in the rejection region for our hypothesis test. We would reject the fact that there's no correlation where it equals 0, and we're going to pick that it's not equal to 0, which means that there is some correlation. We know that the correlation coefficient is greater than the critical value because the critical value, as I just showed you, is 0.707. Based on the preceding results, what can be concluded? Should the data from women and the data from men be considered together, or do they appear to represent two different and distinct populations that should be analyzed separately? If I were looking at this data, they look very much like they don't have anything to do with each other. They have the same shape, but the values are far apart. It doesn't actually make sense to draw a line from the men to the women when the women are all clumped together and the men are all clumped together. I'm good with there are two different populations that should be considered separately. Let's just read through them. The two data sets are the same population and they should be considered separately. Not for that reason. There are two different populations that should be considered together. I disagree. The two data sets are the same population and they should be considered together. I'm going to go with A, and that is the correct answer. They just really don't seem to have anything to do with each other. Listed below are numbers of internet users per 100 people and numbers of scientific award winners per 10 million people for different countries. Let's just get our StatCrunch open first. Let's answer them one by one. First, stat, regression, simple linear. We have our data is internet users versus award winners. This is our hypothesis test. Everything here looks good. Let's look at our scatter plot. That's going from 30. Let's change our x-axis is going from 30 to 80. And our y values are going from 0 to 12. Now let's look and compare the two plots. We have this one dot down here that doesn't look like A or B. It looks a lot like C. I have that dot, and then I have these two dots, and then I have three dots straight up and down. Here we go. It is C. Check answer. Perfect. The linear correlation coefficient, we're going to get from right here to 3 decimal places. And now let's determine the null and alternative hypotheses. For the null, it's rho equals 0. And for the alternative, it's rho is not equal to 0. And check answer. The test statistic, it is right here, t-stat. We don't use the one for intercept. We only use the one for slope. We want this to 2 decimal places. And the p-value for the slope to 3 decimal places, 1, 2, 3. Now we have to decide what it means. The p-value of the linear correlation coefficient 0.064 is greater than the significance level. There is not sufficient evidence to support the claim that there is a linear correlation between internet users and scientific award winners. Notice here, I cannot reject rho equals 0. I do not have enough evidence to support the claim that there is linear correlation. Check. Let's grab this. Listed below are annual data for various years. The data are weights in metric tons of imported lemons and car crash fatality rates per 100,000 population. Let's find the claim. The null hypothesis is always going to be rho equals 0. And the alternative is always going to be rho does not equal 0. This is always going to be a two-tailed test. Now, when they want the scatter plot, we can go to stat, regression, simple linear. We'll grab those values, compute, and let's go to our graph. It doesn't look like this. Do you want to put it on the same axis? That'll make it easier for us to tell. I'm just clicking here, by the way, on these 3 dots, and then going to x-axis, and the x-axis is going from 0 to 600, and then my y-axis is going from 14 to 17. And now it should be easier to tell what it looks like. Definitely doesn't look like that. It looks a lot like that. Doesn't look like that or that, so I'm gonna pick B. I go back. The linear correlation coefficient R equals, this is actually negative here because we saw that line was going down. Let's look again. It's got a negative slope. If that wasn't a negative value, we would have done something wrong. And our test statistic, t-stat, again, we're looking for the one for slope to 3 decimal places. And the p-value. There's my p-value right there. Again, I only care about the one for slope to 3 decimal places. It's 20. Because the p-value is less than the significance level of 0.05, there is sufficient evidence to support the claim that there is a linear correlation between lemon imports and crash fatality rates for a significance level of alpha equals 0.0. Do the results suggest that imported lemons cause car fatalities? Remember from the lecture, we talked about causality. Because two things are linear correlated, it does not necessarily mean one causes the other. The results do not suggest any cause-effect relationship. That's not it. That's not it. That is not it either. It could have been something completely different. And in general, there's not a cause and effect relationship, even if two things are linearly correlated.